Okay, so welcome everyone. Thank you for joining us. Today we have the pleasure to hear Jean-Luc Lehners, who will tell us, will update us on the no boundary proposal. Please.
Thank you very much. And thanks for the invitation to give this talk here. Yes, in the talk, I want to just give a bit of an overview of the no boundary proposal. And by this, I mean that I would like to first review the main idea and then also review early works on the no boundary proposal. And then in the last part, I will spend more time on recent developments and especially also on work that I've been involved with myself. Okay, so the first part will really be review and then newer things at the end. The reason for the title is that the first mention that I am aware of the idea of the no boundary proposal is from almost 40 years ago. It's from a conference which was held in Rome, in the Vatican, and funnily enough, they sometimes have these scientific meetings, and there was this meeting on cosmology, and the Pope John Paul II gave an allocution at the beginning of the conference, and you can read about it in the proceedings. And he was saying that well, actually here I can evidently I can just read it in French, though I have to see if I can see my whole screen. For some reason, sorry, I cannot manage at the moment to see my entire screen. Okay, so he was saying, toute hypothèse scientifique sur l'origine du monde, comme celle d'un atome primitif, d'où dériverait l'ensemble de l'univers physique, laisse ouvert le problème concernant le commencement de l'univers. La science ne peut par elle-même résoudre une telle question. Il y faut se savoir de l'homme qui s'élève au-dessus de la physique et de l'astrophysique et que l'on appelle la métaphysique. Il y faut surtout le savoir qui vient de la révélation de Dieu. So there you have it. So the Pope was saying that in fact, this is a question that one cannot hope to be able to answer. So this was an optimistic start of the conference. And then at the same conference, Stephen Hawking did propose precisely this idea, where he said, this paper considers the questions of what the boundary conditions of the universe are and where they should be imposed. He says it's difficult to define boundary conditions at the initial singularity, and even if one could, they would be insufficient to determine the evolution of the universe. This is, by the way, this is because of large quantum fluctuations. So he's saying, if you try and impose conditions near the Big Bang singularity, it will not be reliable because you have such strong quantum fluctuations that these initial conditions will be meaningless. And then he says, in order to overcome this problem, it is suggested that one should adopt the Euclidean approach and evaluate the path integral for quantum gravity over positive definite metrics. If one took these metrics to be compact, one would avoid the need to specify any boundary conditions for the universe. So here he presents the idea that, if you do this sum over compact Euclidean metrics, then this would determine the boundary conditions for the universe. And it would then at the same time replace the Big Bang. Let me introduce the idea once more from a slightly different perspective, which I find to be helpful. Now, you see, in cosmology, we always want to know what happened at earlier times. But let's say we have found some new theory of what happened in the early universe. Then, of course, we want to ask again, what came before that phase? We go to the beginning of that phase and we say, what happened then? And, then we find some new theory for what happened before. And again, we go to the beginning of that phase and we say, what happened before that? And this becomes an infinite regression where we can always ask what happened before. And one way to avoid this is precisely this idea of rounding off the universe, of closing the geometry of the universe. And it's important to keep in mind that this means closing the universe in a four-dimensional sense. So in space and in time. And if you do something like that, then this infinite regression, which I just mentioned, is simply bystepped. And also the initial singularity is avoided. And moreover, as Hawking was saying, one may not need to specify any further boundary conditions. The thing, though, is that with a Lorentzian geometry, this simply cannot be done. If you have a Lorentzian geometry, you shrink it to zero size, you get the singularity necessarily. Now, so you need a Euclidean part of the geometry which allows you to round off the universe, a bit like a sphere, simply like a sphere. Now, that was the paper which I mentioned, which is almost, so this conference was almost 40 years ago. This was just the main idea, but there were very few equations in that paper. Just sort of conceptual ideas. And then the whole proposal was spelled out in much more detail by Heartland Hawking in their very famous paper that followed in 1983. And so in this paper, they give what they think is the definition of the no boundary proposal. So let me just mention it to be clear what the original idea was. So they say the wave function of the universe should be calculated from a path integral, which is defined as a sum over compact regular Euclidean metrics. Now, so in a sense, there is just the final boundary, but there is no boundary at the beginning of the universe. And and moreover, the idea from the beginning is that the path integral should be calculated with the Euclidean action and summing over Euclidean geometries. Now, there are some immediate consequences from this. Now, one consequence, hi Daniele. One consequence is that the wave function should automatically be real, because if it's defined over real metrics, then it will be real. And moreover, the hope was that the wave function should be unique, that this definition was sufficient, to provide an unambiguous mathematical definition. The next point is that really this was also the idea that this should represent the ground state of the universe. Because you see, if we think back towards the early universe, the universe was simpler and became simpler and simpler. The geometry became flatter. The distribution of matter becomes more and more homogeneous and isotropic. So everything becomes simpler. And from this comes the idea that it may well be that the universe is in some sense in its ground state. And then by analogy with quantum mechanics, this corresponds to looking at past Euclidean times. So for instance, in quantum mechanics, time evolution is given by factors such as e to the I et, where e is some energy eigenvalue. Now, if you rotate to imaginary time tau, you see this becomes e to the capital E tau. And then if you imagine taking the limit where this tau, this imaginary time, goes to the far past, then all these factors become massive suppression factors. And the only thing that will survive is the term which has the lowest eigenvalue of the energy. That will be the term that will be left over. And so if you do such a path integral and you sum over the far past in Euclidean time, the idea is that you automatically pick up the ground state. The other thing, and this I will discuss in more detail in a minute, is that the wave function should give different probabilities for different initial conditions. And in that sense, it really is a theory of initial conditions. And finally, topology change can be incorporated, because if one has Euclidean metrics, the idea is that one can add processes in which the topology of the space-time is changing. Now, also from the beginning, it was discussed by Hawking and Hartel that this means that the wave function, when the universe has zero size, should be non-zero. Because you see, it's exactly at such points where the size of the universe shrinks to zero where the topology change is happening. So then, if there are contributions from other topologies, one should see them precisely because the wave function at zero size should be non-zero. Now, that were sort of the early expectations. There were also some immediate, how should I say, puzzles with this proposal. I will just preview three main puzzles, which I think are especially relevant. Now, the thing is that really when you think about this definition of a sum over compact regular Euclidean metrics, it looks like this definition really is in some conflict with the uncertainty principle. The reason is the following. You see, if you want to impose that the metrics are compact, this means that at some point, the metrics have to have zero size. So somewhere the scale factor A needs to be zero. But if you look at the Friedman equation, in a closed universe, I mean, spatially closed universe, here it is. This +1 term comes from the spatial curvature. A is the scale factor of the universe, phi is some scalar matter field, and there could be lots of other matter fields. Now, but if you look at this equation and you go towards this point where A is zero, you see then if you want this Friedman equation to still be satisfied and not to blow up, so in other words, if you want that the metric remains regular, you need that A dot squared plus 1 is equal to 0. Or put differently, you need that the derivative of the scale factor with respect to imaginary time is plus or minus 1, which is just another way of saying that you need a Euclidean geometry near A equals 0. But you see now what the problem is. You want to fix both that A is equal to 0 and that A dot is plus or minus I simultaneously. And you cannot fix a field and its momentum at the same time in quantum mechanics. And so there is some conflict there, right, which somehow needs to be resolved. Now, a second problem, which was clear from the beginning.
Sorry, Jean-Luc?
Yes.
Just a question. Wouldn't one expect that the equation is only valid for expectation values?
That's right. But they, in principle, in particular, the equation should be valid at the saddle point of the path integral. And the saddle points are supposed to give the dominant contribution to the path integral. Mm-hmm. And so it's true that you only want it to be valid there, but you see but you need to define and at the saddle point, because this is a classical solution of the equations of motion, it can be satisfied. Both conditions can be simultaneously satisfied. But the question is, how should you define your integral? When you define the integral, the definition should not be in conflict with the uncertainty principle. So the trouble is, how do you mathematically, how do you define it? How do you say that you sum over compact and regular metrics? It sounds like you cannot demand both at the same time. In fact, we will see that this turns out how it is, really. I will get back to this point several times during the talk, so then maybe it will be clearer. But it's really a question about the fundamental definition that needs to be addressed. Now, the conformal mode problem.
But on the other hand, wouldn't you say that in any path integral, in fact, you don't require this regular property of the paths, right? Typical paths are completely irregular. Maybe.
Oh, absolutely. Yes, absolutely.
So why would you demand such a thing that is not even true in much simpler systems?
But it is not demanded of the whole path. So the whole path would be the whole 4 manifold of the universe. And that certainly you expect that certainly off shell, it will be completely irregular. Already in quantum mechanics, the trajectory of a single particle is not even differentiable off shell. But you see, you still need to have so in fact here it's just so the question is, what do you impose on the no boundary point? So this would be like just the end point of the path. So the path integral really goes between 2 3-dimensional hypersurfaces, typically. But now you say you don't want the original hypersurface. You want this to be gone, or at least be a point. And the question is, but you still need to put some mathematical condition there. How do you say that you want either there to be a point or that you want there to be some regular condition? Ideally, you would want to put both conditions, that it starts at 0 size and that it is regular. And what I'm saying is there's a conflict in that sense, because you cannot impose those 2 conditions simultaneously. Later, off shell, the trajectories can do anything they want. But it's So in the standard path integral, it's the same situation that you go from, for instance, if you think about the double slit experiment, you say you go from point A, the source, to point B, the screen, on the other side of the slits. And so now you've just imposed a condition on the position on both endpoints. In between, the path can do crazy things, but you fix the endpoints. You could also have fixed the initial momentum and the final endpoint, or the initial and final momentum, or whatever. But you cannot fix both the initial position and the initial momentum. That's the analogy. Yeah, so maybe it will become more obvious as we go on. Okay, and yeah, so the other problem, which was known from the beginning, is what's known as the conformal mode problem. So if you take a standard Robertson-Walker metric, you put it into the action for gravity, and you add some scalar field phi, you see the scale factor has a kinetic term, and this kinetic term has the opposite sign in front of it as the kinetic terms for the matter fields. This has been known for a very long time. This is just a manifestation of gravity being an attractive force. But the trouble is that you see now, if you work with the Euclidean path integral, then this weighting factor which you put in, it's completely unbounded above and below. So it looks like you cannot avoid a divergence of the integral. And this is, in fact, this turns out to be the case in concrete models that have been studied. Okay, I will also come back to this later on and how to address this problem. The final issue is that it was hoped from the beginning that the definition was unique, but then in early studies by Halliwell and Luco, they meet in mini superspace, so where you look at a metric with only a few free functions, then they immediately saw that there was a whole range of boundary conditions and integration contours that they could choose. And it was not clear which one should be chosen. Okay, so it was certainly not clear if it was unique, and also if it was not unique, what should be the correct choice. So that was, I would say, the starting point. Then, of course, people started just exploring this. And the way that this was done in the early explorations really was by taking a very pragmatic approach, which was to just focus on the saddle points. So at the saddle point of the path integral, the action is stationary. And if the action is stationary, that means that you are looking at solutions of the equations of motion. However, these solutions could be complex equations of the classical equations of motion. Now, and the reason for doing this is that if that the saddle points should provide the dominant contribution to the path integral. Basically, what you're doing is you're doing a saddle point approximation to a path integral, which is justified because as long as the action is large, so as long as, and this is guaranteed by the fact that h bar comes in as a small parameter. Now, you see, if you just focus on the saddle points, you immediately evade these problems which I was just mentioning, because at the saddle point, since you're looking at a solution of the classical equations of motion, you can specify both the field values and the momenta. Also, because you do not look at the full integral, you don't see the conformal mode problem. And finally, uniqueness may not be a problem. It's only a problem if there really exists multiple inequivalent saddle points. So first one has to see if that's the case or not. Now, okay, so the first result of all these studies was, I guess the most important result was that these appropriate solutions, the appropriate saddle points, actually exist. They are often represented in this particular way, where you say that you first evolve in Euclidean time, tau here, the real, so I'm plotting here the complexified time plane. Here on the horizontal axis is imaginary time, and then in the other direction is the Lorentzian time. Basically, you represent the instanton by the fact that, you know, along the Euclidean direction, it looks like approximately half of a 4 sphere, and it is basically Euclidean. And then as you go along the Lorentzian direction, it becomes more and more, the geometry becomes more and more Lorentzian. It becomes a bit like the sitter space. And even though in general the fields really are complex valued, they become more and more real. And but in general, once a scalar field is added, the geometry really is complex, and that's why I have this yellow region here in between, where really the evolution is most complex. And for this, because it was realized that the geometry is typically complex, they were called fuzzy instantons, because at first it was thought that usually they were just a little bit complex, but mostly the fields were real. Now, I'm giving you an example here of a way of representing such a solution. What I'm doing here is, again, I'm plotting the same complexified plane of the time coordinate. And then on the left panel, we have the scale factor of the universe. On the right panel, the scalar field. And the dark line is just where the fields take real values. So where the yellow regions are where the field is completely complex, and where there is a black line, the field takes real values. So you can see for the scale factor that indeed near the origin, which is often called the south pole of the instanton, this is the very bottom of the instanton, there is a dark line here where the evolution is essentially real. So that's this sphere part. And then it's in between, it's completely complex. And then there is a line which is approximately vertical here, along which the solution becomes more and more Lorentzian. Okay, and for the scalar field, it's very similar, except that in general, even near the bottom of the instanton, the scalar field is already complex, and then it just becomes real at late times. Now, this was just a description of one such solution for one final value of the scale factor and scalar field. If you think about evolution of the universe, so of a universe that grows, then in fact, you need to look at a sequence of such instantons, where the universe becomes bigger and bigger, and at each moment, in a sense, you have to calculate the appropriate no-boundary instanton. So you get a whole sequence of instantons. And then it was discussed from also already in the late 80s that if the resulting wave function, as a function of the final size of the universe, for instance, if this is of WKB form, meaning that it has a slowly varying amplitude and a fast varying phase, then you can assign an approximately conserved probability, which is just mod psi squared, to the associated history. Okay, so you have a whole history of evolution of the universe, which is described by a wave function. And if that wave function is of WKB form, then mod psi squared can be used as an approximately conserved probability along that entire history. Okay, so in that sense, you get... Yes.
How do you normalize this probability? Like, what is
you cannot normalize it. It is not known how to normalize it.
So, okay, so it's not a probability then.
It gives relative probabilities, I should say. Yes.
Yes. So what is the relative to what? Like one wave function, one scale factor is more probable than another
one. One history would be more probable than another history. That's the idea.
But here in this setting, the histories are only measured by the scale factor and the value of the scalar field, right?
That's right.
It's just
yes.
mini superspace, 1 degree of freedom.
Yes. Yes.
Okay.
Yes.
Thank you.
Well, in principle, of course, you can do more because this is just looking at the saddle points. So you don't need to evaluate the path integral. You just need to find appropriate solutions of the equations of motion, which satisfy the no boundary conditions. And so it would also work with, it can also work with more complicated metrics and more complicated matter configurations. But yes, so I should really say relative probabilities because there is no known way in which to normalize the probability distribution. And so the interpretation that has been given so far is just that different histories get different weightings and so different probabilities compared to each other. Now, now then the question is, does the wave function automatically reach this WKB form? And it turns out that's not true. So you need some kind of attractor mechanism to actually achieve this, that the wave function becomes semi-classical. Now, the best understood example of this is precisely inflation. And if you have inflation, for instance, if you have slow roll inflation, then you can certainly see that this will happen. Because in slow roll inflation, you can calculate the action of a slow roll solution, and it's given here. There is a weighting factor, so an amplitude of the wave function, which goes as e to the 1 over v of phi, where this v of phi means the value of phi at the bottom of the instanton. And if you have a slow roll solution, then this value at the bottom of the instanton will not change much as the universe evolves. So indeed, you do get an amplitude which is varying very little. On the other hand, the phase goes like a cubed. So where a sub f here is the final value of a. And so as the universe grows, the phase changes in proportion to the volume of the universe. And this factor grows exponentially fast. Okay, so you can see that you indeed immediately get this characteristic that you have a fast varying phase and a very slowly varying amplitude. But it turns out that's not the only possibility. So there is also another mechanism, which is aparosis, which interestingly enough can also provide no boundary instantons. So there, these instantons look quite different. The bottom part, which was the sphere in the inflationary case, is also a sphere here, except that the sphere is very large. It's so large that it looks very flat. Then there is an extended region over which the fields take complex values. And then as the universe contracts, the geometry becomes more and more Lorentzian. In this case, the weighting of the wave function also goes as e to the 1 over v of phi, except that it's the absolute value of v of phi that you need. I'm saying this because aparosis, in order to work, needs a negative potential. And moreover, it needs a steep potential. And then again, you find, so I also give you an example here at the bottom left. Again, you find that that as you approach the final value that you're aiming for, if you would zoom in, you would see that these curves become more and more vertical, these curves where the fields take real values. So you indeed get a more and more Lorentzian geometry. However, in these models, I should point out that what is less understood is how you connect the contracting phase to the current expanding phase. For this, you need a bounce, and it is, I would say it's still not clear if in full quantum gravity a bounce can occur or not. This is something that many people in the world are working on, but I would say it's still not completely settled whether this really works or not. Now, okay, so let me just recap a little bit what I was just saying is that, so the point is that the universe does not become classical automatically, and it does not become classical under any conditions, but the right conditions need to be there. So for instance, if you have a scalar field with a potential, then in those regions where the potential is positive and flat and where inflation can occur, indeed, a classical universe can emerge. Or if you have regions of the potential where it's sufficiently steep and negative, then via aparosis, a classical universe can occur. But in other regions of the potential, the universe simply does not become classical. Now, also, what comes out of these studies is that because the probability, the weighting goes as e to the 1 over v of phi, you see then that small values of the potential come out as preferred. And this has the implication that typically one would say that the probability for short periods of inflation is bigger than long periods of inflation, and also the probability for long aquatic phases is bigger than short aquatic phases. This fact that normally you predict that inflation only lasts for a short time has led to the fact that some people have argued that one needs to use the anthropic principle then to explain why the universe has the shape that it has, and maybe even that one needs eternal inflation to explain why inflation lasted as long as it is hoped that it lasted. But I would say that this is still a bit premature to argue in this manner, because it seems to me that this understanding of probabilities is still quite heuristic. I mean, as we just discussed, for instance, it is not known how to normalize the probability distribution, but also it is just an approximate definition of probability that is used, and only in some sense at late times when the universe has already become classical. And so it is not completely clear that this is already the full answer to the question of probability. So I would, in my view, this is something that still deserves more work. Oh, no, I want to mention one other aspect of these early studies, which in fact, this is a very nice aspect of the no boundary proposal. And that is, if you look at perturbations around these saddle point geometries, then I'm giving here the example of tensor perturbations called H here. And I'm here, this is already after performing a Fourier decomposition. So looking at spherical harmonics with wave number K. Then this equation has two solutions in general. And one solution happens to be regular at A equals 0. So where at the origin of the universe, then, and the other one blows up there. So basically one is forced to choose the regular solution. And this regular solution is precisely the Bunch-Davies vacuum of the perturbations. So that means that the no boundary proposal automatically explains the Bunch-Davies vacuum of perturbations, which is something that is normally put in by hand in calculations in inflationary models. So I think this is a very nice feature, that you do not need to explain the vacuum state of the fluctuations, but it is determined automatically. Let me just point out, because this will be important for what I'm discussing next, that there is a subtlety in this discussion, in this calculation of perturbations. And this is the following, that as we saw, the no boundary saddle point solutions are complex solutions of the equations of motion. But the equations of motion themselves are real equations with real coefficients. So if you have a complex solution, its complex conjugate is also a solution. But it turns out that that complex conjugate solution has very different physical properties. So there is one solution which leads to this weighting, which goes as e to the plus 1 over vacuum energy. But if you take the complex conjugate solution, it has an amplitude which goes as e to the minus 1 over lambda. So the physical predictions would be completely different for these two cases. And what I described so far was one could call it the Hartle-Hawking geometry. The complex conjugate then is the tunneling geometry that has been considered in Vilenkin's tunneling proposal. And one way to think about these complex conjugates is the following, that as you go back in time along the Lorentzian time direction, you see you have to rotate time to get to the Euclidean or imaginary time direction. This is the standard Wick rotation that you perform in quantum field theory. And for the Hartle-Hawking solution, this Wick rotation proceeds in one direction. And for the complex conjugate solution, it proceeds in the other direction. So it's like doing a Wick rotation but not turning right, but turning left, if you like. And this has consequences for the perturbations, because in the Hartle-Hawking case, the perturbations obey a Gaussian distribution, which has a weighting which goes as e to the minus h squared. So this is a simple Gaussian, and this is in agreement with what we observe in the CMB. Now, in the other case where you take the complex conjugate background, the tensor perturbations are unsuppressed. In fact, you get an inverse Gaussian distribution, e to the plus h squared. And this is a problem, of course, because it means that larger and larger perturbations would be preferred. And that means that, in fact, you would need to include back reaction, you would need to see what happens for large perturbations, but basically the model breaks down. Okay, the assumption that we had a nice homogeneous isotropic background with small perturbations around it certainly breaks down. Okay, so bearing that in mind, I come to more recent developments. And the recent developments in some sense are sort of reconsidering mini superspace versions of the no boundary proposal and trying to look at them in a perhaps more systematic way. Now, so again, we will consider an integral over gravity and a cosmological constant lambda. There's a particularly useful way of writing the metric in which the scale factor squared is denoted by q, and the time coordinate is rescaled by this factor of 1 over q. And n is the lapse function, which determines the time evolution. Now, the reason for doing this, for taking a metric like this, is that if you do that, the action for q becomes quadratic. So the action for the scale factor of the universe is simply quadratic. And that means that one can explicitly do the path integral over q because it just becomes a Gaussian integral. There's now still the question, how do we impose the no boundary condition? Now, the first thing to try is to say, well, let's say that the scale factor at t equals 0 is 0. Okay, then we ensure that the universe starts at 0 size, and this then ensures that we are summing over compact metrics. Now, as I said, one can do the integral over q exactly, over the scale factor, and then one is left with an integral only over the lapse function n. Now, this is a complicated integral, but it can be analyzed, for example, using a saddle point approximation. So we can look at the saddle points. There are 4 of them, which are all complex. And then we can look at their steepest descent lines. So here I am plotting the plane of the lapse function. And so there are 4 saddle points in orange, 1, 2, 3, 4. These 4 saddle points have their steepest descent lines emanating from them, and everywhere steepest descent and ascent lines. And I'm indicating the direction of descent with the arrows. So the arrows always point to, a downwards amplitude. Now, okay, let me point out something first that I wanted to say next, but I think it's logically better to say it first. I should explain that in green, I am denoting regions where asymptotically the integral is converging. In red, regions where asymptotically the integral is diverging. And yellow are in-between regions. You see, if you now want to define the integral along the imaginary axis, which would correspond to a Euclidean path integral, then there are these red regions, either near the origin or here near large values of the lapse function, where the integral simply diverges. So you cannot define the integral along Euclidean metrics because it just becomes infinite, and mathematically it does not exist. So you have to choose another integration contour. So one could, for instance, take this orange line here, which is just the Lorentzian contour along real values of n. Now we can deform this contour to run through a steepest descent path, which is just this path J1, which passes through the saddle point 1. So really there is just one saddle point which contributes to this path integral. And that's just this saddle point 1. And this, it turns out, is one of the unstable saddle points. So this is one of these saddle points which are actually the complex conjugate of the geometry that you want. The stable ones are in the lower half plane. The unstable ones are in the upper half plane. And so this means that if you define this integral now along the, to be over Lorentzian metrics, because you cannot define it to be over Euclidean metrics, you find that it gives an unstable result. Now, moreover, you see, you could choose a different contour which would pass through the saddle point, a stable saddle point. For instance, here, the saddle point number 4. But you see, there's a steepest descent path which goes from this stable saddle point directly to the unstable saddle point. So if you include the stable one in your integral, you will automatically include the unstable one too. And that means that the instability is still there in your calculation. There has been some debate in the literature over what one should do in this situation and whether one can still define the integral in this way or not. I refer to the papers mentioned here at the bottom for this discussion. For the sake of the present talk, I want to simply show you that there is a way of avoiding this discussion altogether. Now, as I said at the beginning, there seems to be this conflict.
Sorry, Jean-Luc?
Yes?
Sorry, one more question. I don't know if it's best to answer it at this point or later, you choose. But are there problems or reasons not to consider contours which are symmetric with respect to positive and negative laps? Because those will correspond from the point of view of the path integral to solutions of the Wheeler-de Witt equations.
Yes, yes. So you can definitely do that. You can choose. In fact, you can choose either to solve the propagator equation or to choose the Wheeler-de Witt equation, the ordinary Wheeler-de Witt equation. But the issues are the same. So you can, if you, for instance, if you take the Lorentzian contour along the entire Lorentzian line, there is a singularity at n equals 0. So because you cannot get from the original no boundary point to the large universe in 0 time. That's why there's a singularity there. You could now either let your contour go above this singularity, then you pick up both unstable saddle points, or you can let it go below the singularity. Then it turns out you pick up all 4 saddle points. Then your contour will be sort of going along to saddle point 2, then 3, then 4, then 1, and out to infinity. So, but the problem is that whichever you do, whenever you get a contour in which, it does not matter which contour, if it's an infinite contour or a half infinite contour, any contour that picks up a stable saddle point will automatically include the unstable saddle point. That's the real problem. But you can choose but you can certainly choose to have a symmetric path, integration path, and I will give an example in a minute of that.
Okay, so from this point of view, there's no real reason to choose one over the other.
No, no.
Okay, good. Thanks.
Yes, so the way to resolve this problem is the following. We said at the beginning that there is there's kind of this conflict with the uncertainty principle. And you see, now we try to just fix the initial size to be 0. What you can do instead is just fix the regularity condition. So fix the condition on the expansion rate, and just fix that the expansion rate is Euclidean initially. Now, if you do that, you see this q dot has to be imaginary because it has to be Euclidean. But now you have a choice of sign. You can say it's plus or minus I. And that's the thing, that this choice of sign effectively fixes the Wick rotation. So if you fix this to be plus I, then you automatically choose the stable saddle points and you eliminate the unstable saddle points. They're simply gone, right? So if now I look at again, the same drawing as before, we only have 2 saddle points left, which are the stable ones, and the steepest descent paths have rearranged themselves. So now this J3 and J4 are the steepest descent paths which run through the saddle points. And now you can in fact choose an integration contour which is just the full Lorentzian line. There is no singularity anymore at 0. But the full Lorentzian integral can be deformed to be the sum of this J3 and J4. So it will pick up both saddle points. And again, the Euclidean integral would not work.
Sorry.
Yes.
Can you show us again what the action for laps was, so that we better appreciate how this change of choices affects your
I think I did not write it. Let me see. So this is the integral when you fix the initial position, the initial size of the universe, sorry. And you see you have this 1 over n factor here. And that's why you get this pole at n equals 0. I did not write what the integral
I
is.
see. So Q
With
dot
other
now
conditions.
replaces Q1 basically.
But
The
this
structure
term
is
is gone. Yeah, this term is gone. There is also an n squared. There's an n cubed, an n squared, and an n term, and actually even a constant term. But there is no 1 over n term anymore.
So it's basically the result of the Gaussian integral with different boundary conditions on
Yes,
Q.
exactly.
That is
That's exactly it. This gives a different dependence on the lapse function, and it eliminates the pole. And you see here, this effectively, this equation, if you take, now you look at stationary points, you get an n squared term, a constant term, and a 1 over n squared term. So effectively, this is a 4th order equation. You get 4 saddle points. When this term is gone, you see you get just an equation in n squared when you look for stationary points. So you're left with just 2 saddle points. And this is because you've really eliminated the 2 unstable saddle points, because they do not respect this boundary condition that you impose.
very nice, thank you.
And so now, but still the Euclidean integral is impossible, but the Lorentzian one works. And the other point, which is important, is that at the saddle points, even though we did only imposed a condition on the expansion rate of the universe, at the saddle points, nevertheless, the geometry closes. So the geometry is compact and regular at the saddle points. Now, that definition, you see, it was motivated from the cosmological point of view. It was just motivated by eliminating unstable saddle points. Then we realized that actually this is the exact same condition that one has to put on path integrals in anti-de Sitter space. So if you look at path integrals with a negative cosmological constant, in anti-de Sitter, normally you put a boundary at spatial infinity, or far at a spatial location far away, and then you send it off to infinity. But in the interior, you have to sum over interior geometries. Now, these interior geometries also have to be regular. And it turns out that one needs to put the exact same regularity condition in the interior than the one that we had put for the no boundary proposal. What this means really is that these ADS and DS path integrals are the same if you analytically continue the vacuum energy lambda. This also means that but you see the ADS path integral, you know what it has to be because of ADS CFT. So it corresponds also to a partition function in a conformal field theory. And so, in fact, from this, you can know exactly what the result is. And in the ADS case, the wave function is this airy BI function given here, where lambda is really negative here. But you see from what I just argued, this should be the same as for positive lambda. So you can do the analytic continuation of the airy BI function, and it becomes an airy AI function. And so this is the result here for the wave function. Now, in the case of a positive cosmological constant. Now you can learn some more from this correspondence. And this is by looking now at the saddle point approximation of these integrals. So this is the full result, but the full result also tells you what kind of contours of integration you should have chosen. And on the ADS side, I'm plotting here, again, the 2 saddle points that one gets, n plus and n minus. Here they are just when you let the final radius be 0 size, and then you increase the final size, then the n plus saddle point moves up, the n minus saddle point moves down. And I'm also plotting next to the saddle point, I'm plotting the associated geometry. Now you see this n minus saddle point starts at a 0 size, so also a vanishing geometry, and then the geometry grows. And you see the n plus saddle point is different. When you say that the universe is of 0 size, this saddle point is already a sphere, because the sphere again goes to 0 size. And in fact, this saddle point encodes the topology change. So when the universe grows, it is always a sphere connected to a growing universe. But this exact result of the wave function tells us what the contour of integration should be, and it is such that only this saddle point n minus contributes. And so this means that these topology changing geometries do not actually contribute to the path integral. One can do the same thing now on the de Sitter side. And here there is a kind of a new phenomenon that occurs. So again, one has the n minus, n plus. N minus starts at 0 size, n plus starts as a sphere. But now as the universe grows, the two saddle points first move together and join, and then they separate and turn into two saddle points which are complex conjugates of each other. So in fact, what I was showing before in this graph, you see now we already have that here the final size of the universe is already large, and we have two saddle points which are complex conjugates of each other. But not complex conjugates of each other in the same way as before, that it leads that one is stable and the other one is unstable. Rather, in this sense here, the geometry is the same, but the direction of time is reversed. Now, in fact, what I just explained before, that in the ADS case, you can see that the topology changing transitions do not contribute. That means that this n plus saddle point does not contribute. So you do not get the contribution to the wave function of the universe from these sphere configurations. And only the saddle point n minus contributes at first. But when the universe gets large enough, this one relevant saddle point splits into two saddle points which are now both relevant. And this is known as a Stokes phenomenon, where you go from one relevant saddle to two relevant saddles. And when this Stokes phenomenon happens, that's exactly when you add a Lorentzian part to the geometry. So that's exactly when time emerges. So in that sense, the Stokes phenomenon is necessary in order for time to emerge in this context. And so you really go from one relevant saddle point when the universe is very small to two relevant saddle points when the universe is bigger. So one more thing which I would like to point out is that because we said that we impose a momentum condition in defining the wave function, that means that actually the wave function should satisfy the Wheeler-DeWitt equation not in position space, but in momentum space. And so here is the Wheeler-DeWitt equation that the path integral satisfies. But you see, it also turns out that this regularity condition that we imposed corresponds to a specific value of the initial momentum, P0. And this, in this notation, it's minus 6 pi squared I. But you see, if I plug this in here, this value of P, this first factor here is just 0. So that means that in addition to the Wheeler-DeWitt equation in momentum space, there is this additional condition that the wave function must satisfy, which is that d psi by dp, where p is the momentum, is 0. Now this is very nice because it means that you see that the momentum should not change at the no boundary point where the universe comes into existence. That means that there should be no momentum flow into or out of the universe, which is exactly in agreement with this idea that the universe should be completely closed. You know, that the universe should be it should be closed and self-contained. And now you see this condition that I d by dp acting on psi is 0 is the same as saying that the size operator q acting on psi is 0, but where you now express the size operator in momentum space. So really this is just the condition, the 0 size condition, but translated into momentum space. Now I have one final thing I would like to point out, which is that the perturbations in these no boundary geometries behave quite differently from what one is used to in standard inflationary models. So if I look at the solution of just for instance, the tensor perturbation in the usual flat slicing of de Sitter space. If you look at this solution, it's the following. You know, it's at late times when the fluctuation exits the horizon, it freezes, it becomes constant. But if you go back in time, then it oscillated a lot. In fact, it oscillated faster and faster, and moreover, the amplitude goes up. If instead you look at now the time evolution in the closed slicing of de Sitter space, you see the behavior is a little bit milder, but very similar still. It's a little bit milder because at some point you reach the minimum size of the Sitter space and then the amplitude does not grow anymore. But you see the no boundary geometry is a complex geometry in which you reach this no boundary point where the universe is of 0 size and where the fluctuation actually goes to 0. And here I'm plotting what the fluctuation looks like on this no boundary geometry. And you see it's very different. This is the same perturbation mode, same wave number, but it oscillates far less. And in fact, it's highly suppressed as it goes towards the origin. So in some sense, the no boundary geometry really smooths the perturbations. And this again is in good agreement with this idea that really the no boundary describes the ground state of the universe. So in fact, it's the opposite of reaching the Big Bang. It's something where everything becomes extremely mild as you go back towards this no boundary nucleation point of the universe. Now, instead of a big conclusion, because I think I said most of the things I wanted to say several times already. So let me just point out some open problems that still remain in this whole framework. As I already said earlier, I think that a rigorous definition of probabilities is still lacking. And then so far there have been a whole number of sort of post-dictions. So the no boundary proposal can explain the classicality of the universe. It can explain the ground state of the perturbations. But what one would really like at some point is some prediction which really makes it testable. And that's still lacking. The other thing is that almost all of the detailed studies have been done in mini-superspace. And what we really like is to be able to go beyond mini-superspace. And also almost all studies that I am aware of work in an effective 4-dimensional context, whereas we would also like to know, for instance, in a full string theory, does the no boundary wave function exist or not, or what does it imply? Let me just mention that my student Caroline Jonas and we've recently looked at what happens if you just take in for the effective theory where you add correction terms that would come from loops. So where you add terms that have higher powers of the Riemann tensor, and we could show that the no boundary solutions continue to exist in this case, so that if you have these correction terms added, the no boundary solutions are still there. So let me just show you my collaborators on these projects, and thank you very much for listening.
Thank you, Jean-Luc. So we have time for questions.
Yeah, maybe. So what is the status of this debate slash conflict with Hartle and collaborators? Has there been some common ground found in the end, or people are still not convinced of each other's arguments?
I think that I would say that probably everybody by now has their own opinion, and that maybe even my opinion is not the same anymore as that of my collaborators.
Excellent.
No, I would say, okay, so I think in the end, this debate about whether you can impose compactness as a condition has never been fully resolved. So it seemed to us, to Job and Neil and me, that we have shown quite rigorously that it does not work. However, I think that this conclusion has never been completely accepted by the other group of people. But as I said, I think by far the neatest resolution is just to impose a regularity condition instead. It completely eliminates the problem. And moreover, I think that really now that there is strong support for this from this analogy with ADS path integrals. So in that, I would say that in that sense, the problem is simply bypassed. And, but the original debate and question is probably not resolved in the sense that there was no general agreement.
Okay, thank you.
Yes. So I think this is the fairest I can say, that there
it's
is
very fair and very clear.
That there is no real agreement, but I think also really that one can, yeah, that it has become less important now because one can just ignore the problem.
Very nice, thank you. Well, people think of other questions, so can I go with one more? But this time is very, very basic and very, very technical, actually. There's one thing I remember I never got around to understand. In the full theory, usually lapse is can be entirely fixed as a Lagrange multiplier. But
Yes.
Somehow I know with this tidal volume analysis, it's only the time derivative that you can entirely fix, so that you're left with this
Yes.
constant that you can integrate over. But I never quite grasped why there's this leftover non-gauge fixed zero mode. Do you have some intuition for it?
Yes, I think it's kind of it has to be, because it determines the age of the universe, which otherwise would be fixed. So maybe the confusion comes from, so the thing is that in the path integral, let's not think about the no boundary proposal, but simply an amplitude from, say, today to tomorrow for the universe. Well, actually, I should not say from today to tomorrow. Let's say from a scale factor to a larger scale factor. Now, you don't know how much time this will take. And so you need the lapse to be free because it expresses this idea that you are summing over all possible time intervals that this transition could take. And then at the saddle point, you should essentially find the most likely time that it will take for this transition to occur.
So let me put it in other terms then.
Yes.
Why, if I integrate over all possible values of lapse, don't I get a divergence associated with the invariance under time reparameterizations of the path integral?
Well, the integral over the lapse. Okay, so one thing I can say, for instance, is that, you know, an integral over Euclidean values of the lapse does indeed give a divergence. If you integrate over Lorentzian values of the lapse, each history just gets a phase, you know, e to the is. And so you are summing phases, and that integral is conditionally convergent. And then using the steepest descent path, you can make it absolutely convergent.
Yeah, maybe also because, is this related to the fact that we have somehow a preferred clock that comes from the scalar field, or it's completely unrelated?
No, it would be the same without a scalar field. But maybe, okay, maybe let me say it one other way, is that here one chooses a time coordinate in which both the initial and final times are fixed. Whereas what you think about is maybe you can fix the lapse, but then you are not saying what is your final value of the time. But instead you can say my time runs from 0 to 1, but I will not tell you how fast it runs, and the lapse will determine how fast it runs.
Yes.
Okay, so that's the way that we're doing the calculation, that we take a coordinate which goes from an initial to a final hypersurface. That coordinate range is fixed, but how much physical time elapses is then determined by the value of the lapse.
Yeah, okay, I see it. Yes, now I see it. So it comes from the fact that you've chosen the physical interpretation for this initial and final points that you're fixing, the values of time. Right,
you're sort of fixing those values, but you're not saying how fast your clock is turning.
Yeah. I see. So that's what removes the zero mode from the pure gauge direction, the fact that you fix this. Okay, thank you.
Right.
In fact, sorry, I think if I understand correctly, it's exactly like in the relativistic particle. The lapse is basically the proper time along the trajectory, and it gives you the length of the curve.
Yes.
And there's no real difference. Also, in the case of a single particle, you have the reparameterization invariance of that trajectory, but that
right. In fact, we could have
the
talked
total.
About,
Yes, I think it's exactly the same.
Yeah, we could have talked about that. So the question was, what is the physical choice that you make, or the boundary condition that you impose, so that this gauge invariance now has a zero mode that is actually physical and measuring some elapsed time.
So it's fixing the coordinates to have a fixed range.
Yeah. Okay. Yeah, thank you.
Yeah, I did not show all the details of the calculations because, I never know, is the audience more interested in just the general overview, or do they want to see the actual details of the calculations? And so, yeah, it seems for this particular talk, I certainly could have added more details. But
you shot for a good intermediate range, I think.
I have one question. When you say that it would be important to go beyond the minisuperspace, if you go beyond minisuperspace, it means you introduce inhomogeneities. But then you're, no matter how many inhomogeneities you include, you are basically in the full path integral context. What exactly would you be able to compute there? In principle,
honestly,
beside calculation complications.
I have to say that I don't know exactly how one can go beyond minisuperspace. The issue is that the issue is the following, that you restrict by having the minisuperspace ansatz, you have fixed almost everything in the metric. I mean, you just allow for some free functions, but you've basically fixed, or you've turned off all sorts of inhomogeneities. But the trouble is, again, the question is, again, is there a problem with the uncertainty principle? Because when you turn them off completely, but according to the uncertainty principle, you should not be able to turn them off completely. You can either say they have zero value, field value, or zero momentum, but you cannot just turn them off completely. And the question is,
in other words,
something important?
Yeah, sorry, in other words, the homogeneous configurations are effectively singular from the point of view of the full theory.
But
it's like choosing a delta function as a wave function in the full theory, and that, of course, is not integrable even in a generalized sense.
Now, in a geometrical sense, the minisuperspace should have some value, because if, let's say, you imagine just integrating over all sorts of manifolds without restrictions, but you see here we show that the very homogeneous and isotropic universe is the most favored, and perturbations around that fall off. So at least you show that this is in some sense a consistent framework, right? Because the perturbations really are suppressed. But of course, you have not now done the sum over all possible manifolds, right? Nevertheless, at least it seems then plausible that this most symmetric configuration being the most favored, that this will remain true. But well, nevertheless, yeah. So the thing is that because one is ignoring a lot, it is never clear that this was, whether there could be interesting effects associated with that. And of course, it would be great to find out what is being ignored here.
No, but I think my question was less clever. I think I was just asking that, at the purely technical level, the moment you introduce inhomogeneities, you go out of the function setting and you would really have to deal with functional issues.
Yes.
Because
yes.
And so you need some strategy to at least do part of that. And I was wondering what the strategy was supposed to be.
Yeah, this I actually don't know. I just, yeah. I honestly, I don't know what how one can really handle this. If I knew, I would do it.
If you know, let us know.
Yes. We can agree on that.
we have our strategies in different contexts, but if you find any other suggestion,
no, of course. But what I mean is directly now in this path integral framework. Yeah, this is one of the unsolved problems, clearly.
Thank you.
Thanks. Okay, are there more questions? Okay, if not, we can thank Jean-Luc again.
Thank you very much.